The truck weigh station on I-75 is an opportunity to practice the MM1 model in queuing theory. So if you've actually downloaded these note frames, you might notice that just for convenience sake, the formulas associated with that model are sort of snuck in on the last page. Now, we're kind of skipping ahead here because let's look at the problem itself. All trucks traveling on I-75 south of Ocala, Florida must stop at a weigh station. This station has one set of scales which can weigh an average of 18 trucks an hour exponentially distributed. Trucks arrive at the weigh station an average of 15-hour Poisson distributed. This business about exponential arrivals, exponential distribution, Poisson arrivals, and there only being one server, that's actually how I knew with confidence that this was the so-called MM1 model. Now, the MM1 model is nothing more than a series of formulas that you can learn all kinds of things about the truck weigh station, but you need lambda and you need mu. Lambda is the mean of customer arrival distribution. I mean, that's just what it is. And lambda was quoted to us. This is important. Where was lambda? Let's see. Trucks arrive at the weigh station an average of 15 per hour. That is perfect. Lambda equals 15 per hour. Now, we also need, in order to manipulate these formulas, because we'll be doing that very, very shortly, we need this factor mu. Okay, and it's the companion of lambda. It's the mean of the service distribution. That's what I'm jotting down here. And this is important. That means we need a number. You notice what I wrote? A blank per hour. We need to know, okay, this is a weigh station. We need to know then on average how many trucks can be weighed per hour. Mu is always the number of customers that can be served in a time interval. It's never a length of time. Oh, all right. Now, I think that actually was in the paragraph. Yes, there's a single set of scales which can weigh an average of 18 trucks per hour. That is perfect. That is mu. Oh, all right. Now we're all set to go. We're all set to go to answer these questions. What was the questions? Let's see. A. What is the average delay a truck suffers at the I-75 weigh station? That is, what is the average total time the truck spends waiting and being weighed? So this is all one question. It's asking for one estimate right here. All right, one of the keys to using the MM1 model is knowing which formula essentially answers one question. This business about find what is the average delay that the truck suffers overall, that's on here. I've got to find it. That is, oh, it's right here. Average length of visit to the system. That was what was being described. Or W sub S. One way to remember it is wait, right? Delay. S, system, overall, not just in the line. And the formula that we were looking at was WQ, wait a minute, that's the weight in the line, plus 1 over mu. All right, so this is the formula we need to answer this question. Of course, wait a minute. I know what mu is. We were just saying that was 18. What is WQ? WQ is another formula. WQ is on this sheet right above it. I'll copy it over here. Okay, well, WQ, the average weight in the line, is LQ, the average length of the line, divided by lambda. Lambda, I know, that's 15, except wait a minute, what's LQ? Yes, that's another formula. You can find it there on that sheet. That's the average length of the line. That one, at least, is lambda squared mu times mu minus lambda. I'm just copying it back here. Oh, right, so at least I know these numbers. And yeah, you know, to answer this question, it's kind of a daisy chain. We need this result to put in here, to get this result to put it in here, and then this would actually generate the answer to the question. Oh, all right, well, we can do that. We just have to back up. It's just ironic, this one question. We just have to back up all the way to L sub Q. First calculate what's the average length of the line. All right, let's see. LQ is 15 squared over 18 times 18 minus 15. I get, comes out kind of messy, repeating numbers, but 4.1667 basically. Oh, all right, so what I just discovered here was that on average there's a little bit over 4 trucks in the line at this particular way station on I-75. All right, but that's not going to answer the question I'm working on. But I do take that number and backing up towards the left, let's see, then that means that 4.1667 divided by, okay, lambda is 15. W sub Q is 0.27778. Oh, okay. Then take that number, backing up, finally, 0.27778 plus 1 over 18. I get 0.3333333 some odd. This particular problem is a good example of the type of problem that if you're getting like slightly different numbers off of that, it doesn't mean that you're doing anything wrong, because we have all these repeating decimal places. You can get these slight variations depending on how many decimal places you actually store in your calculator before you go on to the next step. Anyway, so have we answered this question? Well, actually, yes, we have. Because we wanted to know the average delay that a truck suffers at the I-75 workstation, and we now have this reading, 0.3333. This is important though. What is that supposed to mean? Hours. How did I know that? Because whatever lambda and mu refer to, when you're calculating lengths of time like WQ or WS, remember that what you see on your calculator when you're finished is in that same time interval. Our lambda and mu were per hour, so 0.3333, you know, we finally have W sub S is in hours, 0.333 hours, which isn't very intuitive. Most of the time, if you told somebody the wait will be 0.33333 hours, they would kind of pull a blank. That's very easily translated into other measures. For instance, 0.3333 times 60, there's 60 minutes in an hour, would reveal that's the same thing as essentially 20 minutes. Oh, okay, so the average total delay at this station for a truck is about 20 minutes. All right, fine, actually, so finally we've answered just this first question. Let's see if the second question goes any faster. What is the probability that an arriving truck will have to wait? Good thing to know here. Probability of waiting is the same thing as system utilization. I said, well, why is that important? Because that's actually what the label is generally and what the formula is referred to. System utilization, the percent of time the system is busy, is very easy to calculate in the MM1 model. It is just lambda over mu. So in our case, it's just 15 over 18 or 0.83333, or basically, it's just a nicer way to say it, 83%. It's explained as utilization because 83% of the time the one set of scales at this way station is busy, but that is the same thing as any truck, right? If you were to drive up to this, that is the same thing as the chance that you'd have to wait because the scales are busy. Okay, got it. On average, how many trucks are waiting in line at the I-75 workstation? Way station, workstation. Wait a minute. We have a formula for that. That is average number of customers in the queue, LQ. That is a description of how many trucks are waiting in line of LQ. Now LQ is lambda squared divided by mu times mu minus lambda. And you can put the numbers in here, but at least we could make some use of the work we had to do for the first part of the problem. We actually calculated that already. Yay. We were remarking it's like a little bit over 4 trucks. That's the average length of the line in front of the scales. Okay, good. That one's done. 2 others. On average, how many trucks are at the I-75 weigh station? How many trucks are, and they said, no, didn't we just do that 4.1667? That was how many trucks were in the line. This includes any truck that's being weighed as well. It's just like the total population at the station. The symbol is L. It's still a count, but L sub S for total number in the system. There's LQ, right? We said, well, we know that. And then down below it on this particular formula, there's LS. Oh, and it's not unrelated to LQ, because what you do is you take the average length of the line and you add lambda over mu. All right, now I did that. The 4.16667 plus, we'd seen lambda over mu before, that's 15 over 18. It basically comes out, actually, ironically, then fairly neatly, 5. Those are trucks. What we've just discovered is that this particular weigh station south of Ocala, Florida, if you just look over there, on average, there's 5 trucks there, right? One of them, if there's any trucks there, is getting weighed, but on average, count them all, there's 5 trucks there. Oh, all right. So, now, is the last one going to be fast? What is the probability of no more than 3 trucks at the weigh station? Oh, this is not going to be fast. It's not going to be difficult, but it's not going to be fast. And here's why. Look at our formula sheet. Probability. We have 2 formulas for probability. We have a formula for the probability of no customers in the system. That, for this problem would be the probability of no trucks at the weigh station. We could compute that. We have another formula for the probability of n customers, meaning you pick a number, 1 customer, 2 customers, or 3 customers exactly. We'll fill out this formula. It would give you the probability. Notice that this question here, the thing that's challenging about it is it doesn't ask about any exact number of trucks, like what's the probability of 2 trucks at the weigh station. It asks for what's a range. It says no more than 3 trucks. The way that we can do this, the way to tackle this though, is we have to break it back down to exact situations. Okay, a situation in which there is no more than 3 trucks. What does it include? Well, it includes, and I would need the probability of no trucks, right? Because no trucks fits the description of no more than 3. Okay. I also need the probability of 1 truck. Because if there was 1 truck over there, that fits the description. I need the probability of 2 trucks. Because if there were exactly 2 trucks over there, that would fit the description. And I need the probability of 3 trucks. Exactly, because if that was true, it would fit the description. Anything else, 4 trucks, 5 trucks, 6 trucks, does not fit that description. If I add all those up, that would get me the probability of no more than 3. Because basically I've accounted for every situation that would count, that would fit that description. So what I wrote here was just kind of a verbal conceptual model, but now it becomes a work list. I've got to actually find out those numbers. Now the probability of 1 truck, that's pretty easy. P sub 0 equals, from our formula sheet, 1 minus lambda over mu. So in our case, 1 minus 15 over 18. or 0.1667. So right there, what we know is there's like a 16-17% chance at any given time of there being no trucks at this way station. All right, now that's a piece of this. We have to find the other pieces. What's the probability that there happens to be exactly one truck? All right, now here's where we want to use the general formula. I'm going to copy it over from the formula sheet, but you can see it on the formula sheet. The probability of some certain number n equals the, and this is handy because we already found it, the probability of none times, again, lambda over mu, but to the power of n, the particular number that you're interested in. It's this expression that I need to now employ 3 times to find these 3 other probabilities. So the probability of 1 equals, now let me think, p sub 0 we now know is 0.1667 times 15 over 18, that's our lambda over mu, to the power of 1, which is to say times 15 over 18. All right, well that comes out super messy, but 1, 3, 8, 8, 9, it's what I see on my calculator. Oh, all right, so that's the probability that there's 1 truck over there. What is the probability that there's 2 trucks over there, exactly 2 trucks? Well, you take the 1,667, because that's p sub 0. You take the same 15 over 18, but you square that before you do this. Okay, well, I did that and I got 0.11574. Okay, there's about 11-12% chance of exactly 2 trucks being there. And then finally, what is the chance of exactly 3 trucks being there? 0.1667 times the same 15 over 18, except cube it before you do this calculation. The result, 0.09641. Oh, all right, now what do I have here? I have a series of scenarios and their likelihood. There's like a 16-17% chance you look over at the way station and there's no trucks there. There is, for instance, about a 9 going on 10% chance you look over there and there's 3. What was the question? What's the probability that there's no more than 3? We add these up. So if you add these up, pretty messy, 0.517747 is what I was seeing on my calculator, or basically, just talking about the odds. What's the chance? That's essentially 52%. So you glance over at the way station. What is the probability at least there's no more than 3 trucks there? It's about 52%.